Okay, let's start, because it's a dense presentation, very technical. So my name is Jean-Philippe Bempel. I work for Qteo for a year and a half now. Previously, I was working for a company that's on the financial market, so we're writing orders to the market in less than 100 microseconds, not milliseconds. So when in Java, so if we have a GC, GC is obviously an issue with this kind of application. So when there was the first low latency GC was coming up with Azul in 2011, 2012, I jumped in and to use it in production, and also trying to figure out how it works internally. So you can ask questions on Slido, GeeCON 2019, room 12. And so we will try in this presentation to see how the GC works. So I'm assuming here that you know how basic GC works with the mark phase, sweep phase, compact phase. So I will not re-explain that. What we'll do is to explain the concurrent marking that is common for all the new GCs. Then we will dig into Shenandoah. That's one from Red Hat. Then Azul C4. That's my biggest part because I know well this GC. And finally, ZGC. That's the newest one. And we will explain how to choose between those algorithms. So concurrent marking is the common one with all the low latency GC. So when I say low latency GC, is to reduce the post time. Who here is annoyed by the post time of their GC? Okay, couple. Okay, so you're in the right place. So for concurrent marking, that's the common part for all the GC. It's not new because we already use concurrent marking for CMS, concurrent mark and sweep, and G1. So we already use this kind of techniques. So the technique is to try to mark the whole object graph concurrently with the application. So your application is still running, the thread of your application are still running, and you want to have this part of the GC concurrently to save the post time. This concurrent marking is based on tricolor abstraction and the snapshot at the beginning algorithm. So let us explain what is the tricolor abstraction. You have an object graph with the GC root on the top left. So the algorithm is to traverse this object graph from the GC root. So when we have all these objects not unmarked, they are all white, then we begin with the GC root, we mark it gray. Then we'll proceed for all the children of this object. There is only one, and we mark it gray. And since we have marked all the children of the first object, we can then mark it black. Then, recursively, we proceed for the other object of the graph. So we take all the children of the gray object, this one, we mark it gray, and then all the children are marked, then we mark it black. And finally, all the children are marked also black, no children. So they all are completely marked and traversed. There is only one object white because there is no reference that point to this object. So this is garbage. And we want to get rid of it. If you perform this concurrently, there is some issues that can arise. You can miss some object because your application thread can modify the object graph. So first issue is the allocation, new allocation. If you allocate new object during the concurrent marking, how to deal with that. There is two options. The one is to mark automatically those objects as live. Okay, so that's when you are allocating up, you mark it live. That's simple. And the other one is not considering those new allocation. So you allocate in a new region or new address space don't take care of this object for the current GC cycle. The nice thing about the tricolor abstraction is they get you two properties for missed objects. So it characterizes when you miss an object concurrently. So if you have a missed object, it's because you have those two properties in this. So the mutator is the application thread. So if a mutator stores a reference to a white object into a black object, and if all the path from a gray object to a white object are destroyed, you have a missed object. Let's take an example. We are concurrent marking this object graph. We are in the middle of marking the object B, and we have this code executed by an application thread. So we are storing into a field of object A a reference to C, okay? And then we are removing a reference, putting null into the field 2 that pointing to C. So we are storing into a black object a reference to a white object, and we're destroying all the paths from a gray object to a white object. Oops, we missed the C object. So now, in this situation, we cannot reach the C object because the A reference C, we are not marking through the A because it's black, and the gray object have no relation and no path to the C object. So C object will be considered as garbage, and still we have a reference to this object. So how to deal with this, how to resolve this issue? There is two ways. One is the snapshot at the beginning. That's one technique that we'll describe right now. And the other is incremental update that we'll see later. So for SATB, so snapshot at the beginning, the JIT will insert new code. So we call it pre-write barrier. So it means that when we assign an object to a field, so we're writing, before this assignation, we will do some process. And this barrier is only active when the concurrent marking is active. Okay. So the pseudocode of the JIT what will be inserted for each assignation, it would be that the check of this write barrier, SATB write barrier, if it's active or not, and then if the destination field is different of null, then we enqueue this field into a queue that will be processed afterwards. So it means that for every assignation, reference assignation, we will have an overhead of code that will be inserted by the JIT to take care of the problem of the concurrent marking. So, for example, this kind of code that the JIT will insert for each assignation in your code, okay, automatically. So we have a comparison on the two first line that say, okay, it's active or not, and if the concurrent marking is active, then they will execute the rest of the code, and there is also a call at the end, call to subroutines again. So there is some quantity of code that are executed for each assignation inside the concurrent marking. So that's it for the concurrent marking. Let's do it for Shenandoah. Shenandoah was started by Red Hat in 2013. It's open sourced, now included into the JDK 12. Okay, you can use it with some backport on JDK 8 if you get the OpenJDK build from Red Hat. But beware, because since the JDK 12 it's inside the OpenJDK for OpenJDK, but not with the build from Oracle. So if you get the OpenJDK build from Oracle, you cannot use Shenandoah because it's not supported. So you need to get it from another OpenJDK vendor or Red Hat. So Shenandoah GC, what is it? It's a non-generational GC. That's new for a JVM because most of the GC in a JVM are generational. But there is still an option for partial collection, so partial collection of the object graph. It's a constant for all the low latency GC. It's a region-based, so not a big block of allocation for each generation. Now we have separated region like in GeeCON. Constant also for all low latency GC is the usage of a read barrier. We call it a Brooks pointer for Shenandoah. We will explain this later. Self-healing, that's a notion, a concept that was introduced, in fact, with C4, but I think it's relevant for all the low latency GC because it's a constant for all those GC. It's the cooperation between the application thread and the GC thread. But for Shenandoah, it's only for the concurrent compaction phase. So when we compact, it's when we are moving object from a region to another. So the self-healing process will be only for concurrent compaction. So the Shenandoah GC is mostly based on GeeCON. So if you know how GeeCON works, basically that's very similar, except for the concurrent compaction, or there are some subtleties, I would say. So what are the Shenandoah phases? First one, initial marking, that is top of the world. Then the concurrent marking, so it's very similar to CMS, so SATB style or GeeCON. So that's what I described earlier. Then we have the final remarks, top of the world phase, to catch up with all the reference that was changed during the concurrent marking. So the queue that I described previously is processed, if not completely drained at that point. We have concurrent cleanup. Concurrent cleanup at that stage, it means that if a region is completely free, it will be immediately reclaimed and used for another location at that point. So if there is no object to move in this region, they will be reused for allocation. The concurrent evacuation, that's the part where we are moving object from a region to another to evacuate this region and to be able to reuse this region. That's a tricky part. Then we have a stop the world for preparing the update of references. It means that as we have moved objects into the memory, we need to update all the references to those objects to be consistent. There is a part for concurrent update references, and then the catch-up. And then, finally, we have the concurrent cleanup where we can reclaim the freed region and use for a new allocation. So let's dig into the concurrent evacuation. That's the tricky part of this algorithm. At first, we have the same principle than in GeeCON. It means that we have built the collection set with the garbage first. Okay, that's where the GeeCON is coming, garbage first. So we sorted all the region that we want to collect, and we begin with where there is most garbage because there is less object to move. We evacuate those region to a new to release the old one. The concurrent evacuation will be done with the help of read barrier, one read barrier, let's call it a Brooks pointer, and 4 write barriers. So we saw previously that we use a write barrier for the concurrent marking. There are also 4 write barriers for the concurrent evacuation to be done. Those barriers help to keep the two-space invariant. So what is the two-space invariant? Is that all writes that we made into an object need to be into the two-space two-space region, in fact. So we have the from space and to space. From space is the source region, and to space is the destination region, where we are moving the object. So it means that when we need to write the data into the field of an object, it needs to be into the destination and not into the source. And those barriers keep it ensure that we keep those invariants correctly. So what is Brooks pointer? So all objects have an additional forwarding pointer that is placed before the object right now. So we have a regular object with the header, and then we place a Brooks pointer just above. And this Brooks pointer basically will point to the beginning of the object with the header. That's the place. So each time we need to access an object, we need to pass through the forwarding pointer. So we need to dereference the pointer, Brooks pointer, to get to the object each time we access the object. So it means that we have memory footprint overhead because the objects are a little bit more in size, in memory. And then we have throughput overhead because we need to go into this direction each time. So for the JIT, it means that it emits something like this. So we are loading through the Brooks pointer with dereferencing and moving to the register R13 here to get the address of the object really. And then we can access the object. So what happens during the concurrent evacuation or copy? Once we have the GC thread that's dealing with this object. So we have here a from space, so the region, the source region, with an object that needs to be moved to the to space, the destination region. So we have a GC thread that's taking care of this object. There is no concurrency with the other application at that point. So that's the normal or nominal case. So in this case, the GC thread will copy the object to the to space and then update the Brooks pointer to the new destination. So if an application thread tries afterwards to point to this object, to access this object, we will go through the Brooks pointer and get into the other on the object into the to space. So that's the classic way. If we now have some reader threads from the application that need to access this object that needs to be copied at some point. So those reader threads will get the object from the from space and try to access via the Brooks pointer, and Brooks pointer point to the same object. So as this is the reader thread, we are not breaking the to-space invariant because we are not writing into the to-space, we're just reading. So the read can be performed into the from space without problem. Now, the tricky part. We have writer threads that want to write concurrently into this object that is in the from space. So all the two writer threads here will copy the object into the to space in two different locations in the to space, because each of the writer thread will copy his own object, and then they want to try to update the Brooks pointer concurrently for their own copy, but only one will succeed. It's a CAS operation, compare and swap operation. It's a classic lock-free operation, and this there is only one that will succeed, and the other will fail to update the Brooks pointer. For the writer side that failed to update this Brooks pointer, it will roll back the copy, reread the address from the current Brooks pointer, and will access the object that was copied by the other thread. So when we want to write field into the object, we need to make sure that it's correctly copied before, because we are breaking the two-space invariant. So we need to copy this and make sure that only one thread have updated the Brooks pointer correctly, and then the other threads can write and access to this object through the Brooks pointer that was updated correctly. So that was the tricky part of this algorithm. Now, for the write barriers, so I will said, any writes, even for primitive, so if you have an in field, there is this write barrier that will jump, and to make sure that we have not break the two-space invariant. So that's the pseudocode of this write barrier. So if we have an evacuation progress, and if it's, the object is in the collection set of the region that I want to evacuate, and then if there is not copy yet, then we evacuate this object like I said previously. So that's the kind of JIT that was JIT code that was emitted for each write barrier. So for each write, we have to test if the evacuation is in progress, and then all this code, the two other tests, to see if we need to perform this copy or not. So it's add overhead for this, but just in case of evacuation in progress. But still, we need to test from memory if the flag is activated or not. There was also 3 other exotic barriers for write barrier for pointer comparison, but not so much in Java, for cast, compare and swap, and clone. In extreme cases, we have in Shenandoah a late memory release. If you look into the phases, you have the concurrent cleanup, and it's at this point that we have we can reclaim those regions. So we can reclaim those regions only when all the references are updated. So it's very late into the phase of the GC. So we can have some problem with allocation that are too fast and overrun the GC. So to deal with this kind of extreme cases, there is 3 failure modes. The pacing. So the pacing is inserting some thread.slip into the application thread to paste those threads and trying to finish the GC cycle. Degenerated GC, it means that if we are in a situation where there is no more memory, we can stop all the application thread and finish the GC cycle of Shenandoah during the stop the world phase. So no more concurrent phase, all are in a stop the world phase. And then the classic full GC, if all those previous failure mode failed. So C4 now. So C4, when I think about C4, I think about explosive because my father was a military. But C4 instead stands for a continuously concurrent compacting collector. It's a generational collector, so you have the young and old generation. Again, region-based, they call it pages. We are using read barrier. But another kind, it's called loaded value barrier. There is a self-healing process, again, cooperation between application thread and GC threads, but at multiple levels. The algorithm that was published in 2005 is pauseless, really pauseless, but the implementation in hotspot requires save point. It means that stop of the world phases, but very few. In my experience, pauses are most of the time below 1 millisecond. Okay, the maximum I saw in my application was 2 milliseconds. So LVB means loaded value barrier. That's the read barrier. I will explain how it works. That's a Baker style barrier versus the Brooks pointer that we saw in Shenandoah. It means that we move objects through the forwarding addresses stored aside of the heap, basically. So in a Brooks pointer, we are storing the forwarding pointer in just above all the object. For the Baker style, we are storing those forwarding address aside in some arrays, tables, aside of the heap. And we applied this read barrier at load time, not at dereferencing time, okay? That's the biggest difference. Load time, it means that when we load the reference, not when we go through this reference. Ensure C4 invariance, so this barrier makes sure that when we reach an object and when we load the reference on an object, it is marked or not for this current cycle. And if it's not relocated, if we are not moved this object if needed. So if those invariants are broken, there is a self-healing process to correct it. So in case of an unmarked object, we are marking the object, obviously. And if it's not relocated, we relocate or moving the object, and then we are updating the reference for the next time we'll go to the new location and not going to the same process again. So this barrier is checked for each reference load. But with the JIT optimization, we can get some caching value. So for example, for a method, we have multiple access to an object, to the same object, but it can be cached into registers. We apply the barrier only once and can access multiple fields into this method without the cost of each access with the LVB. In this, the state of the object are stored into the reference address. We call it caller pointer. So inside your 64 bits address or reference, you will store, you have some bits that are not used because the 64 bits address space is very huge, and some bits are not used. So they are using those bits to store some information. For example, the NMT bit, so not marked through bit, to indicate if the object is marked or not for the current GC cycle, and also the generation. So when we check the LVB against this GC cycle, we expect a value. And if it's not, we are breaking the invariant, and we need to correct this by marking, for example. So this global state is either a thread local or store a thread local. So it means that most of the time we will hit the L1 cache or in the register. So they have changed the way they are storing this global state. Previously it was in thread local, and then they are moving to the register to be more efficient now. That's what the JIT is emitting for the latest version of the Azul. So they are testing two registers, the global state and the current loaded reference. And if it's okay, they can jump. They are accessing the field on the third line. And if it's not okay, they jump into a slow pass to correct the LVB. For relocation, the x86 implementation uses a trap from the VM memory translation guest host. So it's a feature from the CPU vendor that was introduced like a decade now. For dealing with the virtualization. So for Intel, it's EPT, for extended page table, and for AMD, it's a nested page table. So they use this mechanism, in fact, to give like a memory protection. And if we access to this memory, protected memory, they install a trap or a handler, like a callback, that will be used to say, okay, we're accessing this memory, it shouldn't, so we can try to correct this and execute some code to correct this. So let's get a reminder about the difference between virtual memory and physical memory, because we are in use for the next explanation of the algorithm. So we have virtual memory, it's like addressing 64 bits. So it's very, very large. In fact, it's 2 power 64. And we have physical memory that's very more restrained, like in this example, 2 power 37, it's like 128 gigabytes. So it's still very different. There is still much the difference between 37 and 64. So virtual memory can be very, very, very large. And then we can allocate this physical memory, a page of physical memory that can be backed by a page of virtual memory, one-to-one. Another, okay? And we can have another page of virtual memory that could point into the same physical page, so that we can play with virtual memory to do this kind of tricks and say, okay, we can have multiple virtual memory that points and backed by only one physical page. We could also have another virtual memory page that is backed by no physical memory. And if the process tries to access to this page, it will get a page fault. And for example, we get the memory from the disk, that's swap, and bring back to physical memory. So that's normally a reminder. So let's go to the C4 phases. The mark phase, we're marking all objects in an object graph. Basic. Relocation, we are moving object and release pages. And remap, we are fix up references because we have moved objects. So now we need to fix all the references that are pointing to the previous location to the new. For the remap, we can fold this remap phase to the mark phase because we are go through all the object graph, all the objects from the object graph. So as we are traversing all this object graph, we do the same for the mark phase. So we can fold those two phases instead of traversing twice the object graph. So graphically, you can see that the remap phase for the first cycle is merged with the mark phase for the second cycle, and so on. Mark phase. Instead of having the snapshot at the beginning like Shenandoah, we are using the incremental update marking. It means that it is single pass. There is no final remark phase, the stop the world phase, with this way to perform the concurrent marking. And we are using the self-healing process to mark objects that are not marked by the GC thread. So if the application thread tries to access an object and we have the concurrent marking in concurrent, the application thread will mark for the GC thread this object for the current cycle. So let's see how the incremental update is working for resolving the issue that we saw earlier. So still the same. We have an application thread that's trying to modify the object graph. Here, we are loading the C reference. And as we are loading a reference, we are triggering the LVB here. And the LVB say, OK, is the C object is marked? No. So we are marking it. That's why it's gray now. And then we continue to execute. OK, but the C object is now marked gray. So we can continue the processing and mark all objects correctly without losing the C object here. So that's the way the incremental update can resolve this issue, and without able to have a remark phase to process all this, to catch up all the missing references. Relocation phase. That's the tricky part. So for us, G1 and Shenandoah, we are choosing pages that have most of the garbage, that object, garbage first. And then we protect this page from mutation from the application thread. So at this point, all the application thread cannot access to this page and to the object. Then we move object to the new allocated page. We build the side arrays with forwarding pointer. And if a thread, application thread, try to access those protected pages, the LVB will be triggered via the trap mechanism. And then the application thread will copy the object to the new location if not done, and use the forwarding pointer to fix the reference. So let's take an example. We have virtual memory and physical memory, okay, with 2 pages, fill. So we are locating a new page of virtual memory and physical memory. We are protecting the page that we want to evacuate. So we install the trap handler and everything. We are copying physically the object from one page to another. Okay, that's reflecting with the virtual memory. We are installing the forwarding table to say, okay, if we access those objects protected, you need to find them at the new location. And then we can release the physical page because nobody will access those objects because they are already moved. And if an application thread tries to access those objects, it will go through the forwarding table and go through the new location. So we can release the physical memory, the physical page. And then we need a new page to be allocated. And this page in virtual memory can be backed by the new released physical page. Okay, because it's already freed. So as we are still in the GC cycle, we can immediately reuse the reclaim page. So it means that to start the process of a GC cycle, we just need one freed page, virtual and physical, to start the process as a seed and continue the process because we are releasing memory, releasing object, releasing pages, and we can go on and go on. Remap phase. We traverse the object graph, fix up the references to the new location, if not already done. We execute the LVB for each object of this graph. So if this is not correct, we'll correct it via the LVB and self-healing process. So we fix the reference using the forwarding of information. And then as we traverse again the object graph, we mark also this object for the next GC cycle. So at Criteo, it's a web advertisement company, we are using a big Hadoop cluster, like 2,000 nodes. And the problem with this in the architecture of Hadoop is that we have one name node that handles all the metadata files of the files into this Hadoop cluster. And this is a central point and need to be very reactive to not collapse the entire cluster. So as we have a lot of files, we need a big heap, like 580 gigabytes, that was previously running on a regular JDK 8 with G1, but we tend to have a very hard time to tune G1 and not get a full GC. I remind you that in JDK 8, if you have a full GC in G1, it's single-threaded. So for this kind of size of heap, it's like 30 minutes to perform the full GC, at least. So we roll out in production Azul and C4, the Azul JVM Zing. And since October 2017, we have no issue with GC so far. So very convenient to have this kind of GC for this kind of situation. So finally, ZGC. Don't worry, it will be very fast. So at that point, it's non-generational, but they are planning to get a generational one. But for now, it's non-generational. It's also region-based. They call it ZPGs, dynamically sized. They have the concurrent marking, the concurrent compaction, the concurrent ref processing. That's a new thing compared to Shenandoah, not for C4, because C4 have also the concurrent ref processing, but that's That's new for ZGC. Concurrent wave processing is to handle all the spatial references like weak, soft, phantom, and finalizer. They are using the colored pointer also with read load barrier, of course. That's kind of read barrier that you can see in ZGC. So they are using the thread local. That's why you have the R11 register that is used for thread local. So they get the state in R10, and then they test the current reference with the global state like this, and then they can go on. But you have to hit a memory read to get this. The self-healing process, again, you have cooperation between mutator thread and GC threads. It's in JDK 11 in experimental mode. And then, who knows about Cliff Click? Here, okay, a couple of hands. Cliff Click is the man who started the hotspot JIT, and then go to Azul company to work on the JIT inside this company, and also on the C4. And when he get into the ZGC algorithm, they said, okay, it sounds like the same as C4. GPGC is for generational poseless GC. It's another name for C4. So it seems that's very, very, very similar. And in fact, yes, it is. It's very, very, very similar. So I will not go all through the explanation of the ZGC. If you want to understand ZGC, go to C4, basically. There is some difference. For the phases, it's basically the naming that is different, but we have an initial mark, a concurrent mark, and remap. So they are folding also the concurrent mark and remap, like a C4. They have a final mark, stop the world, also, and the concurrent prepare for relocation. That's the part where they are also processing the reference. A stop the world for start relocate, and then concurrent relocation, like in C4, and then we are looping for on the next phase on initial mark again for remap. Color pointer, they are also storing some information in some metadata information in a unused bit of the reference address, again like C4. Currently, they are using 42 bits, but they are planned to use more. I think it's next will be 46, I think. They use 4 bits of metadata, marked 0, marked 1 for either GC cycle, if the reference is remapped, and it's finalizable. So that's the way they are representing the reference address. So 42 bits up to 4 terabytes, and then we have 4 bits for metadata, 45 to 42. And then we still see that there is a lot of 0 at the end of address, so there are still room for storing more information or shifting to get more heap space address. So to access those objects through this color pointer, they are using a technique like multi-mapping to avoid to mask for each reference those metadata, unmask those metadata reference to get the real address and to get to the object. But some hardware are supporting natively, and they have instruction to unmask this for their dereferencing, like Spark or ARM64. So on x86 and Linux and Windows, there is an override with classical instruction. So they come up with an ID based on the fact that there is only one view active, so there is only one bit set on the metadata information. So there is only one bit to unmask at each point. And we have also assuming that we have plenty of virtual space, like we see previously. So how it works. We have one physical memory allocated page, and in fact, for each bit that could be set into the metadata information, we have each time a view that is allocated in virtual memory pointing to the same physical page. So based on the current GC cycle if we have marked or not the object, or if we have remapped the object. We have a different metadata stored into the address, but only one bit is set. So depending on each cycle, we can have access to this address, directly dereferencing it, and in fact pointing to the same physical memory. So if C4 and ZGC are very similar, if there is any differences, yes, but very few. So how they are handling the remapping? C4 is used the memory protection plus trap, as the ZGC use a mask in the color pointer. For unmasking ref addresses, C4 use a kernel module to do this with aliasing. It's like a little bit a black box of this, and for that it's using the multi-mapping or the hardware support. For page relocation, C4 used a page that is fixed and matched the OS size for memory protection. And for relocation of large objects, they are using remapping of the virtual memory instead of moving it. So just play with the physical and virtual memory. For ZGC, Z pages are dynamic, and a Z page can be like 100 megabyte large. But for large objects, there is no relocation. It's like the humongous object in G1. They are considering that it's too costly to move those objects. So finally, how to choose a GC algorithm between those three? If you run on Windows, that's simple. Use Shenandoah. That's the only one available right now for Windows. If you want a very mature, low latency GC that is battlefield tested, I recommend C4, but also Shenandoah that is now very production ready. If you want to minimize other JVM poses than the GC, go to C4 because they have implemented the concurrent wave processing, but also concurrent deflection and other kind of technique to reduce the usage of save point and the size of the poses. And also the GC because they have the concurrent processing, but also the concurrent class unloading, like also for C4. And if you want to not pay for this kind of GC, Shenandoah and Z, because C4 is a commercial JVM. I put into the slides some references if you want to go deeper. So some reference about GC basics. For Shenandoah, for C4, with the algorithm published by Azul, with the poses algorithm and the implementation for x86, the C4. And also the source code at the 2010 time. And for the GC too. And thank you for attending my session. If you have questions, like 2 minutes for the question. Let's see if I can get the word to. No question, seems to. Okay, it was a very deep technical presentation. Sorry for that, but maybe you can look at the records afterward and to have a more deep understanding after that. Thank you. Thank you.